Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solving the problem number 16. Let's consider this network consisting of 4 resistors labeled R1 through R4, as well as one independent current source IS. Additionally, we can observe the presence of a dependent source, especially a voltage-controlled voltage source. The question now is to calculate the value of Vx using Thevenin's theorem. Vx is the voltage across the resistor R1. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with the voltage source in series with the resistor, which will be denoted as VTH and RTH. In our example, RTH is connected in series with the R1, which plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by disconnecting R1 and removing all independent sources in this circuit, which means the voltage source will be replaced by a short circuit and the current source will be replaced by an open circuit. But we see the presence of the dependent source. However, the idea is to excite this network with a voltage VO connected between terminals A and B. We can set VO is equal to 1 volt to make the calculation easy. Our goal is to find the current IO through the terminals. Once we establish the current IO, RTH can be calculated by VO over IO. In order to calculate the current IO, I'm going to use Kirchhoff's voltage law. But first, I will consider I1 is the current through the resistor R3. Now, by applying Kirchhoff's voltage law in loop 1, we can write negative VO plus R2 times IO minus 2 times V is equal to 0. And according to Ohm's law, V, the voltage across the resistor R2, is equal to negative R2 times IO. And if we replace V in the first equation, we obtain negative VO plus 3 times R2 times IO is equal to 0. Or we know that RTH is equal to VO over IO is equal to 3 times R2. And if we replace R2 with its numerical value, we obtain RTH is equal to 15 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage calculated between terminals A and B when R1 is disconnected. In order to find the open circuit voltage VOC, I will apply Kirchhoff's voltage law. By applying Kirchhoff's voltage law in loop 1, we can write negative VOC plus R2 times IS. We don't have current flow in this direction because we have here an open circuit. Minus 2 times V is equal to 0. And according to Ohm's law, the voltage V across the resistor R2 is equal to negative R2 times IS. And if we replace V in this equation, we obtain negative VOC plus R2 times IS plus 2 times R2 times IS. That means VOC is equal to 3 times R2 times IS. And if we replace R2 and IS with their numerical values, we obtain VOC is equal to 15 volt. VTH is equal to the open circuit voltage VOC. That means VTH is equal to 15 volt. Now, in order to calculate the voltage Vx across the resistor R1, I'm going to use the voltage division rule. That means Vx is equal to R1 over R1 plus RTH times VTH. And if we replace R1, RTH, and VTH with their numerical values, we obtain Vx is equal to 5 volt. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here our networks drawn in SPICE simulator. We can see this is the original circuit, and this is the Thevenin's equivalent circuit between terminals A and B. I connect here a voltmeter in order to measure the voltage Vx across the resistor R1, and here I connect a voltmeter in order to measure the voltage Vx across the resistor R1 in the Thevenin's equivalent circuit. Let's move on to analysis. This say analysis calculate nodal voltages. We can see here that Vx is equal to 5 volt in the original circuit and Vx is equal to 5 volt in the Thevenin's equivalent circuit. From the simulation, it becomes clear that the voltage Vx is similar when using both the original circuit and the Thevenin's equivalent. This similarity validates the correctness of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time, another example about Thevenin's theorem. Take care and bye-bye.